All right, guys, lecture 15. This is the good one. All right, I'm going to do something here which I think is amazing. This is Jerry, by the way, back again. Torment you. I want to talk about just complex numbers as we've done so far would have stopped pretty much where we stopped last lecture were it not for the following kind of result, which is called de Moivre's theorem. And this is pretty impressive, actually, and it links different things. It's all based on, let me just write down. Okay, so as I said, this result is the central result in complex numbers, actually. And it's without this, you wouldn't be using complex numbers at all, really. Because, okay, you can do what we did, and that's fine, but really where we're going with it. So this is the idea. This is the important idea in complex numbers, the central idea. So it's all based on Taylor series. I'm not sure if you did looked at Taylor series with Connor. I'm sure you did. And I'm sure Connor emphasized how important they were. And really, Taylor series are the most important mathematical technique in engineering mathematics. Without Taylor series, you wouldn't have engineering mathematics. They're really, really important, Taylor series. And basically what they allow you to do is if you have a complicated function, they allow you to write the complicated function in simple terms at a particular point, if you know how to differentiate the function. Okay, so maybe it's a few rules, a few kind of conditions there. But it's really nice because what you do, you go from complexity into kind of simplicity, provided you can differentiate. So this is like differentiation as a simplifying kind of mechanism. And I don't know if you remember this, but there's a special case of Taylor's theorem, which is an expansion about x equal to naught. Okay, so if you've got a function f of x, you can write that as f of 0 plus f prime 0 x plus 1 over 2 factorial f double 0 x squared plus ... Okay, so this f and f prime 0 and f double 0, this is the value, this is the function at x equal to naught. This is the value of its derivative at x equal to naught. This is its second derivative at x equal to naught, etc. And this x is just x, and you can replace x by any value like that's close to 0. Okay, so this is for x close to 0. Oh, sorry, x close to 0. No, I'm not going to. We're going to skirt over the rules here. We're going to be playing hard and fast with the rules, which is the only way to live, right? Because I'm not going to be interested in convergence, things about convergence, which I worries me actually as a person. You've got this result. But how do you know that when you add up all these results, you add up all these terms on the right hand side, which is an infinite series, you get what's on the left hand side. You know, that's not a trivial result, that this thing converges actually. But we're not going to talk about convergence. We're not going to worry about convergence. We're just going to I'm going to write down the formulas and play around with the formulas and see what we get from the formulas and not worry about the formal mathematics. Okay, which is beyond our course anyway here. But it's a very, very important little idea in mathematics anyway. The difference between engineering mathematics and mathematics, the way I was taught, is that in engineering mathematics, you just do what feels good. You know, just do what comes naturally. Whereas in formal mathematics, you have to justify what you're doing. And that's a different way of thinking about things. Engineers want to get things done. Mathematicians, I think, most want to make sure you can actually do the things that you've been doing. I know it's much more, I don't know, it's not as active. But at the same time, I think for me, it's more intellectually interesting, but that's just stupid tangents. All right. So what we're going to look at this Taylor series, we're going to look at this Taylor series for 3 functions, the most important functions in engineering. One of the most important functions, maybe the most important function, is the exponential. So if you look at f of x is equal to exponential x, okay? And if you were to draw exponential x, folks, at x equals 0, you get 1. Now you can have a negative exponential x. This is how exponential x looks like. And this is 1, and this is x, and this is y, and this is y is equal to exponential x. So exponential x is this kind of very, very quickly increasing function. And unfortunately, these days, what it represents really is the spread of that stupid virus thing. Yeah, it's exponential growth. It's just growing. The numbers infected with this stupid virus is going very, very, very quickly. And if something is growing very, very quickly, it's described by the exponential function. Okay, so this is a really important function in mathematics, and especially engineering mathematics. The other two functions that we're going to be looking at are cos x and sin x. Now, cos x and sin x are basically the same thing. And if you were to plot this f of x here, both cos and sin are waves. Okay, so you just come up and down, and they vary between 1 and minus 1. So the amplitude of cos and sin it goes from 1 to minus 1. So the amplitude is 1. So the maximum value can be as 1, the maximum absolute value can be as 1. So it's a really, this is a beautiful function, actually, and it describes many things that we use in engineering. In particular, this is a very important input into engineering systems. For electronic engineers, it could represent AC voltage. For mechanical engineers, it could be represent some kind of a sinusoidal input that you're kind of a piston input into a system. Whatever it is, it's very common, very useful. And what I'm going to show you now is that if you look at these two functions, these three functions, there's a link between these three functions if you link them using complex numbers. It's just ridiculous. Okay, but here's what I want to do. I want to use this formula here for both exponential x, cos x, and sin x, and see where we go. So let me just do the exponential x first. All right, f of x is equal to exponential x. Now, if you look at the formula here, I need the first derivative, second derivative. So if I differentiate exponential x, I get exponential x. And if I differentiate it again, I get exponential x, dot. So exponential is the function that when you differentiate it, you get back to what you started with. So it doesn't change. Differentiation has no effect on the exponential function. And that's a definition of the exponential function, actually. It's the function that when you differentiate it, there is no change. Okay? But from our perspective, though, what we want to use now is we want to use the fact that we know what the derivatives of exponential x are in our formula here. So we want to get f of 0, so we're going to replace x by 0 here, and we're going to replace x by 0 here, and x by 0 here. So you'll see there for exponential x, folks, that f of 0, I'm going to try and cramp this out here. Exponential 0 is 1. F prime 0, when I place x is equal to 0 here, I'm going to get 1. F double of 0 is 1, etc. Okay? So when I replace x by 0, I'm going to get, when I'm talking about the exponential, I'm going to get 1 here, I'm going to get 1 here, and get 1 here, and if you've got a third derivative, you get 1 there, etc. So the Taylor series expansion about x equal to 0 for exponential x is as follows. So if I go back up here and use the formula, okay, I get exponential x is equal to 1 plus x plus 1 over 2 factorial x squared plus dot. And that's a really important result in applied mathematics, in engineering mathematics. Okay, so let me just kind of summarize it because I lost it at the end of the page. Exponential x is 1 plus x plus 1 over 2 factorial x squared. There's a 2 factorial there. I think you know what the next term is. It's 1 over 3 factorial x cubed. And if you're, you can see the pattern here. It's 1 over 4 factorial x to the power 4. And this goes on forever. Now, as I said, we're not going to worry about convergence here. When I add an infinite, what values of x is this expansion valid for? That's the coffee machine. We're not going to talk about it. Okay, I'm just going to assume that this is true, and we're just going to go with this. This is what Taylor's theorem tells me. I'm just going to go with this. I'm not going to worry about anything else. All right. Now let's look at cos x in the same way. Now I need to differentiate this in order to use Taylor's theorem. So if I differentiate cos x, I get minus sin x. And when I differentiate minus sin x, I get minus cos x, dot. Okay, so the great thing about cos, sine, and exponential is that we know what the derivatives are so that we can use Taylor's theorem. That's one of the great, why they're so useful, actually. So if I replace then x by 0, then I see that f of 0 then, therefore f of 0 is cos of 0, which is 1. F prime of 0 is minus sine of 0, and sine of 0 is 0, so I get 0 here. F double at 0 is minus cos of 0, so it's minus 1, dot. So therefore, if I use this formula here, folks, f of x equal to f of 0, the Taylor series, the general formula for Taylor series about x equal to 0, for cos x, here's what I get. So I'm getting cos x is equal to 1 from this term. There's no x contribution because f prime of 0 is 0 for cos x, and this is minus. So I'm going to get plus 0 times x minus 1 over 2 factorial x squared. There's going to be no x cubed term, because when I differentiate cos, I'm going to get sine, and sine 0 is equal to 0. And when I differentiate sin x, I'm going to get 1. So when I differentiate that, then I'm going to get 1 over 4 factorial x to the power 4 plus dot, 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 dot. So you see what happens. So you see the general formula. So the next term then is going to be minus 1 over 6 factorial x to the power 6, and then it's 1 over 8 factorial, etc. So you see what the pattern is. So if I tidy that up here, I'm going to get 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power 4 minus dot, 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 because the next term is going to be minus. Okay, so you can see what the pattern is. So there's an alternating, it's only even powers of x, and there's an alternating plus and minus. Let's look at sine. Now I differentiate sine x, I get cos x. And if I differentiate cos x to get second derivative of sine x, I get minus sine x, etc. Okay, so I start off with, I'm looking now at sine x. If I differentiate sine x, I get cos x. If I differentiate cos x, I get minus x, etc. So therefore, what do I get here? I get f of 0 is equal to sine 0, I get 0. F prime of 0 for sine x is 1. And f double of 0 for sine x is 0, because sine 0 is equal to 0, etc. So therefore, if I apply my general formula here for Taylor series about x equals 0 for sine x, here's what I get. So I get no constant term, but I get a 1 here for the x. Okay, there's going to be alternating now, like cos, there's going to be alternating a minus and plus. So I get 1 over 3 factorial x cubed plus 1 over 5 factorial x to the power 5 minus dot, 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 dot. All right. So far, so good. Now, this is the stuff that Connor did with you. It's a really important idea. And next year, in second year, we're going to be doing this in 2 variables and in 3 variables, this Taylor's theorem thing, because it is so useful. It is used all the time. Now, I say, you know, after a while, you're beginning to suspect that I am bullshitting you, but saying everything is useful. Without this, without Taylor series, without this formula here, you don't really have engineering mathematics. You know, it's just, it wouldn't work. This is where the action is. So you need to get happy using Taylor's theorem, because it's used all the time to simplify the analysis of engineering systems. And if you don't do it, you can't really simplify. The mathematics becomes really hard if you don't use Taylor's theorem. Okay. So folks, let me just summarize where we are. Okay. So we're using it now. So is this examinable for us? Yes, it is, because this is so important. It bloody well is examinable. Don't even think about it. Yeah, do it. So you need to be able to apply Taylor's theorem, this result here, for different functions. And I might ask you this as well. Okay, Colin might ask you this. I might ask you this because it's so important. I believe in this. I believe in this stuff. Okay, so here we are. Here's where we are now so far. So I'm going to show you what, I'm sorry guys, here. So at this stage, here we are. We've got exponential x is equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus dot, 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 dot. And really, you should probably remember that if you could. I don't know, should you? Maybe you should. Maybe, I think you should. Cos x is 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the power 5 minus dot, 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 because next term is going to be minus. So this alternating plus and minus terms. And sine of x is x minus, hang on, no, hang on a second. This is Jerry, you stupid man. Cos x is square term. Sorry, so this is 1 minus, Jerry, this is so bad. Don't tell anybody, shh, this doesn't happen. It's 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power 4 minus, sorry guys, this is unforgivable really. Having told you it's so important, don't make a shit of it. Okay, so you should remember that. So cos is even functions of x, alternating pluses and minuses. Sine of x is odd functions of x using alternating pluses and minuses. All right. Now, can I ask you this in the exam? You betcha. I can ask you this. I could ask you to get the Taylor series for sine x, derive it. You could memorize it, but I want you to actually be able to calculate it and derive it from Taylor's theorem. Okay? So now at this stage, we've got 3 functions of x, and this is where we were. This was known, people maybe at the start of the 1800s, and people were messing about with this. And then de Moivre, probably a French aristocrat, tired from shooting peasants in the morning, came in the afternoon and said, let's listen. I like these Taylor series, like Jerry, I like them a lot. Let's mess about with these things. So here's what he did. This is really very, very smart. I suppose he noticed, look, that there's somehow that the cos and sine, if you look at the kind of, if you fill in the gaps, this is 1 and you put an x here. So there's the kind of cos and sine kind of fits into the gap between the cos terms. All the sine terms fit into the gaps. If you notice here for exponential, there are no gaps. And I suppose it does maybe make a little bit of sense that he did what he did next, but it is very, very smart at the same time. Let's look at this. Instead of just looking at exponential x, let me look now at exponential ix. Okay, so this is the formula here for exponential, and it's true for all x. So let me replace x now by ix in this formula here. So therefore, the 1 stays the same. I'm replacing x by ix, because wherever, look, on the left-hand side, I've got an x. So on the left-hand side here, I've got an ix. So I need an ix here. Plus 1 over 2 factorial ix squared plus 1 over 3 factorial ix to the power 4. God, guys, dreadful. Plus 1 over 4 factorial ix to the power 4 ... Okay? So all I've done there is, in the expansion for exponential x, I've replaced x by ix. And so this is what I get here. So I get 1 plus ix plus this. And now I'm just going to multiply out, because I know that I squared is minus 1. So what I get here now is I'm going to get 1 plus ix stays the same, plus 1 over 2 factorial. Ix squared, folks, that is just I squared x squared. This is I cubed x cubed. This is I to the power 4 x to the power 4, etc. Okay, because you can bring the power into each of the terms because you've got multiplication. Now, if you look at the first term here, ix squared, which is the same as I squared x squared. I squared is minus 1. So this thing here becomes minus x squared. Here, guys, I've got I cubed x cubed. I can write that as I times I squared x cubed, right? That's exactly the same. I squared is minus 1. So this is minus I x cubed over 3 factorial. The next term here, folks, this is I to the power 4, which is the same as I squared by I squared. And I squared is minus 1, and minus 1 by minus 1 is plus 1. So what I get here then is 1 over 4 factorial x to the power 4. And then you see here this alternating. Okay, so, and then you get in the next terms. Okay? I think that's okay. Now, let's get all the real parts together and all the imaginary parts together, okay, from this messing about. So what I do here, let's get all the real parts. So this is real. because there's no I. This is real. This is real. And okay, so that you get 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power 4 dot 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 whatever the next real term is, plus I into x minus 1 over 3 factorial x to the power 3 plus whatever the next I term is. Now here's the amazing thing, you beautiful babies. Look at this, look at this. This is just phenomenal. The real series here, this infinite series here, 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the power 4 is exactly the same as cos x. And this thing here, after the I, the infinite series multiplying the I, is x minus 1 over 3 factorial x to the power 3, and it's exactly the same as sine x. What? How is this possible? So therefore, the conclusion is, this is the important result, boys and girls, is exponential x is equal to cos x plus I sine x. Oh my God. How does this work? How does this work? This is just amazing. Yeah, it's just this is the most important result in complex numbers. Without this result, you don't have complex numbers. Really, you don't have complex analysis. All right, so this is so beautiful. And there is, and if you think about this, guys, this is just too frightening. There's something mystical here, because what you're doing is you're combining exponential, which we've talked about, and kind of describes the growth of diseases. Cos and sine are waves. So how can they two things be related? And especially, how can they be related? How can waves be related to exponential when you've got I, which doesn't exist? It's just a made-up thing in our brains. So it's just too weird. So I don't know how this works, because when you think about what we're told about the origins of the universe, this is not examinable, by the way. The origins of the universe is not on the exam paper, but the Big Bang, like apparently everything was in a point, and it exploded in this massive explosion, and everything in the universe that we see is a result of that explosion. But in that moment of explosion, this was encoded in the universe. What? Come on, this is just too weird. Folks, I don't know where this is going, but this is just, this is too much for me. It really is. But there you are. Very important results. Okay, exponential ix is cos x plus I sine x. And the reason why it's so important, folks, is because you're taking cos x and sine x, which are, they're okay, but they're waves, and you rewrite them as exponentials. And exponentials are so cool because they have all these nice properties, which we'll talk about now in a minute. Okay, and the reason why this, as I say, is exponentials are very easy to multiply. They're very easy to divide, and they're very easy to differentiate. So exponentials are cool, really are. Now, cos and sine, and listen, if they're at a party, I talk to them, but they're not as cool as exponential. Okay, and you're taking this thing here and writing in terms of exponential, and I'll show you today, maybe, or even tomorrow, in the second part of this, why the exponential is so cool. Once you have this result, folks, you can immediately write down things like, let's replace x by minus x. My God, this is true for all x. So let's replace x by minus x. Look. Ooh. So if I replace x by minus x, I'm going to get cos of minus x plus I sine of minus x. Yeah. What's cos of minus x? If you go to the log tables, cos of minus x is the same as cos x, because cos is even. And sine is odd, so sine of minus x in the log tables is minus I sine x. Oh my God, so this is the reason why, so this is really, really nice. Okay, so you get exponential ix is cos x minus I sine x. So you can mess about with this now. So this is a whole new area. Look, you can mess about. Look, why don't we now, look, let me call this 1, and let me call this 2. Let me add these two things together. Oh, this is too much. Look, let me add this and this. Let's add the left-hand side. So therefore, exponential ix plus exponential minus ix is equal to 2 cos x, because the sine I sine x is cancelled. So you can bring the 2 over to the other side. You get this result, that cos x is the same as adding two complex exponentials. What? That is just too much. It's too weird, but it's true. So cos x is this, and then you can do the same thing for sine x. You can do the same thing for sine x. Sine x is a little bit more complicated because you must subtract 1 and 2, and you've got an I term here, but sine x is exponential ix minus exponential minus ix over 2i. So you can represent cos and sine in terms of complex exponentials. Now, I don't know what you've eaten for breakfast, folks, but like, come on. Like, did you think when you started today that you would learn something as incredible as this? It's from me to you, gift, a little Easter gift. Okay, so there you are. And so you can mess about with this forever now, actually, because as I say, I'm going to talk a little bit now before we stop about the nice properties of exponential, and then we're going to use them maybe in the lecture next week, or I might call this lecture part 1 if I can get this thing to record. But let me just do one other thing with you. There's this competition, if you can imagine, about formulas in mathematics as to which one is the most beautiful. And some people claim that the following is the most beautiful. I'm not sure if that's true, but let me just show you that here's the contestant, a beauty pageant. Okay, so if I look at exponential ix is equal to cos x plus sine x, it's true for all x. Let me replace x by pi. So let me just do that. So exponential I pi, that is equal to cos pi plus I sine of pi. Okay, because it's true. So this is you got this nice result here. So I'm replacing x by pi. Now I know that sine of pi is 0, and the cos of pi, that's equal to minus 1. So therefore, I can rewrite this as exponential I pi plus 1 is equal to 0. And some people say that that's the most beautiful equation in mathematics. No, I'm not sure if that's true. I have a few of my own that I kind of came up with. I think they're much nicer. But that is pretty nice. And what's kind of strange about this, guys, is that you've got a relationship between pi, the exponential function, I, which is the square root of minus 1, and plus 1, and 0. I'm like, what? So this is linking all these important kind of things in mathematics, all these fundamental quantities in mathematics together in one equation, which is quite nice, I suppose. Yeah, so exponential I pi plus 1 is equal to 0. And again, it's all based on the fact that the structure depends on I, the square root of minus 1, which we've talked about doesn't exist. We've made this up. But when we make it up, and when it just so happens that the universe seems to like this. It's just too much, right? So guys, if nothing else from the series on complex numbers that we're doing here, remember this: you will be using this as you go through your engineering studies. So do not it's just something you need to get into your brains. Complex numbers are useful. They're used a lot, especially in electronics. So you need to get this formula into your brains. So I'm going to stop here now, and I'm going to do another lecture on this formula next time, and show you why this formula is so useful. Okay, thank you very much.